speaker is Radhika Nagpal. She's professor of computer science at Harvard University, and today she'll talk to us about gaming systems.
Hi, everyone. So this will be a little bit different, but along the same theme of trying to create groups of individuals that can work together, creating artificial intelligence that's working together as a collective. So I wanted to start out with two examples from biology that, to me personally, were very inspiring throughout my research. In particular, because we look at these systems and we see a whole system, we don't really see the collective that actually made them. So on the left is a starfish, which you can think of as an organism, but you can also think of as a collective of many, many, many cells, millions of cells that together self-assemble this complex organism. And on the right is a termite mound. You can see it in the back of the curve here. This thing is huge, many meters tall. And the termites that build it are only centimeter scale. So it's groups of millions of termites get together and self-assemble this huge mounds in which they live. One thing that's really interesting and common about these systems is, of course, they have this internal structure, which is really amazing. So you have these collectives that are basically self-assembling with complicated internal structure, but also both of them are self-repairing. So if you cut off the arm of a starfish, it can actually grow that arm back. The mound will actually regenerate. It'll self-repair itself. So both of these systems have collectives that self-repair. And these two are really, to me, very remarkable examples of what very simple individuals can do together. But they're really just one of a really large set of examples that we have in nature with very, very large groups of very, very limited individuals, especially limited in size compared to the phenomena that they're part of, can cooperate to create complexity. So for biologists, these systems remain completely fascinating. And the question you might ask is, how do they do it? How do fish work together? How do termites work together? But as a computer scientist, these are also fascinating because just as Maria and you were talking about, we want to create systems that have multiple robots working together, multiple computers working together. We want to scale them up. How do we design algorithms that can do the same kind of thing? So whether you think of food tracking, or fighting fires, or agriculture, or warehouses, or even a future where we have self-driving cars, right? You now have huge collectives of essentially robots working together. And even in more futuristic scenarios, maybe we can make robots that are the size of insects, robots that can pollinate plants, or we can make our own programmable materials that are like multicellular organisms that can be programmed to take on different shapes. So all of these different examples, we're trying to increase the number of individuals, but likewise, what we're going to expect from an individual is going to be less. They're going to fail, they're going to be unreliable, they're going to have limited knowledge compared to the group size, and that's going to increase. So understanding how to program these things, biology provides a good source for us to look at those systems and say, how do they work? And how could we make them work for us in a completely different setting? For me, another motivation is also just scientific, trying to understand how complexity arises from simple units. How do local decisions that we make as individuals affect the collective? And I think there's just a really big area within computer science that thinks about collective intelligence. And robotics is one way of really testing that out. We can build collectives, and we can see if our theories about them work, which is hard to do with natural systems. We can't go around always messing around with what they do. Okay. So I was going to talk about two projects from my group. We work in a couple of different areas. We work a bit on the theory, and we also work very closely with biologists who study cells and study insect colonies. But the two projects that I'm going to show you are examples where we're using inspiration from biology to design robotic systems, both build the robots and try to program large-scale group behavior, and try to make this relationship between the local behavior that the robot does and the global behavior that we expect the collective to do. So can I have a collective behavior and actually derive the local rules that individuals should run? And can we do this in a rigorous fashion? Okay, so the first project sort of harks back to what I was saying in the beginning of termite mound as being this amazing example of centimeter scale individuals that collectively build things that are much larger than themselves. And what's really remarkable about these systems, in addition to the fact that these robots climb over one of the things that they build and do all kinds of manipulation that's really amazing, what's also interesting is that there is no supervisor. There is no termite that's telling all the termites what to do. So somehow, all of these individuals are able to collectively contribute without even necessarily knowing what the other half of the colony is up to. So if you could do that, you could create an amazing system that worked together together over large areas, which is what the termites are capable of doing. So of course, we also like to build. We like to build our own kinds of towers. But now imagine that we could make robots that could build for us. And they could build in areas that were dangerous. Maybe they could build levees in floods, or maybe they could build things underwater for observation. How would these robots work together? Well, it would be nice if we could do the same kind of thing, make lots of robots, throw them at the problem, have them build not termite mounds, but what we want, but still be resilient and robust and parallel and decentralized the way we have termites, the way we know that termites operate, or to the extent we know how termites operate. So one of our current projects, or long-term projects, have been inspired by termites to try and build robots that can construct. So one of the first challenges, of course, is making robots that can do some sort of 3D construction. For example, climb over the very structures that they build. So putting together climbing, manipulation, and sensing all in one package. So these are our Termes robots. As you can see, they have these specialized kind of wheels with spokes. These are called WEGs. These were actually invented in Case Western University, but also built off of work on a famous robot called Rex. It makes climbing very easy, almost by accident. If you move next to something, you automatically climb it. We try to make very simple robots where the very structure of those robots is easy for them to operate. So using as much mechanical intelligence as we can. So here the robot is actually navigating over the structure, and when it's off the structure, it uses distance sensing, and when it's on the structure, it can look at these patterns. So from a robot's perspective, it has a very localized view of the world. Okay, so the second part, or the third part, besides navigation and locomotion, is manipulation. So it has a very simple arm that can lift up blocks using only one motor, so it just has a sort of spring-loaded hand that automatically opens and closes. And this is just an example showing a little bit more put together. So the robot is moving to a particular location, and then finds a location where it wants to put the block. And the thing to notice is actually, first of all, the blocks look like Legos for a purpose. Robots have a hard time doing precision tasks. So we try to make it as robust as possible. And the robot uses a lot of different kinds of sensing. So when it places a block, it jiggles around the block, it feels its sensor, it tries again. So it tries to compensate for errors that we know it's going to make. It makes errors in climbing, it makes errors in placement, but it uses different kinds of simple sensing behaviors to try and be robust, rather than being perfect from the start. All right, so this is just a video showing an individual robot with all of its pieces put together. So we obviously by hand constructed the staircase. And the robot can pick up a block, climb up this staircase, which it knows the structure of, and then place the block and sort of climb over the place thing that it just placed. So hopefully that gives us a first start towards a robot that can physically do the tasks that an individual would have to do. So the next step is coordination. How do we get multiple robots to work together? And can they build something for us without a supervisor? So we showed that you can actually design compilers that can generate rules for specific types of structures. So you give it a picture, and it generates the rules that the individuals will get that they work together. And the rules sort of look like traffic patterns. It's kind of instructing how the structure will grow. So the key thing is that these robots come and they interact with the structure, but they don't know how many robots there are. They don't know if robots are editing other parts of the structure. So you can imagine there are lots of ways you could create cliffs, or you could create enclosures, or you could block other robots. But there's ways to design rules so that even if many robots operate together and they follow those rules, you'll actually always get the correct structure at the end. So there's different kinds of structures, classes of structures that you can actually design compilers for. So this shows an individual robot actually running one of the rules. So as you can see, it comes to this sort of landing strip, receives a block, which is still being hand placed, and then builds a structure. And the important part is that each time it comes back, it doesn't know what's happened when it wasn't there. So maybe the structure broke and it needs to be repaired, in which case it just looks for something to build. It actually doesn't even detect that there was a fault. It's constantly just looking for something to build. And so if another robot, or grad student, builds part of the structure for the robot, then again it can take advantage of that good situation and build. And this is actually how a lot of the coordination happens And one of the principles that's believed to be true in many ant and insect systems, that they react to past work. Rather than reacting and talking to other ants, they're actually using synergy, or what work has happened in the past to direct what they should do in the future. So this is sort of one of our final experiments where we showed 3 robots working together. The robots are, there's no sort of overhead camera or anything. The robots have all of their sensing and actuation within them. And they're really mostly unaware of each other's presence. They come to the structure and they try to build, and the only interaction they have is to yell, get away, get away, get away. So basically, don't fly with each other. So if one robot is too close to the other, they'll sort of wait and one of them will take a turn. It's basically simple traffic rules. And we can build simple structures like wall structures that we want, maybe more solid structures as well. But you can imagine that the next step would be to make robots that could move around beams, or they could build roof structures, or build multi-story houses, or whatever else you can imagine. Or maybe move around bags or other kinds of structures that we might care about in the environment. But there's still a lot of work to do. So one example you can see here is that each of the robots, of course, compensates for mistakes, but there's still ways in which we don't know how to fix the system. Like, what if one of the robots breaks down and just stands there? Right? Termites will drive away the dead termites. We still don't know how to do robots that can actually do that. So there's still a lot that needs to be done to make this system practical. Okay. So the video I showed you had 3 robots, and of course I was taking inspiration from termites that have about 1 million individuals in the colony. So there's still clearly a big gap between the system I showed you and what we can do. And in any of the collectives that you think of, hundreds to thousands of individuals can cooperate. So one question is, what would it take for us to create robot systems at that size? We'd like to be able to experiment them, to test the different kinds of algorithms, task allocation algorithms, for example, like Maria was suggesting, on larger numbers of robots. And then maybe we discover also what parts of our model do we need to consider. So if you have 1,000 individuals, is that same as 100? Is that same as 10? Or are there failure modes that we've just never seen before? So both programming and building robots at this scale is still something really hard. And one of the goals in our group was to try and create a first level test bed in which we could do these kinds of experiments. And we called it the kilobots. And the idea was, can you buy robots in kilos? So how do you make 1,000 robots? Keep forgetting how to do this. Okay. So one key aspect of making 1,000 robots is cost. So if you have a lab, maintaining and keeping 1,000 robots is quite a bit of work. So we use a number of different interesting ideas. So we use cell phone vibrators for motion. These reflect IR off of the line, so they have wireless communication and sense distance. But they can basically do the things you expect a robot to do. You can program them, they can communicate with each other, and they can move. And once you have those basic elements, you can actually put them together in many different kinds of group behaviors. So these are just showing some examples where one robot is orbiting a bunch of other robots by measuring distances, one where it's moving straight. And these kinds of behaviors, people have studied in swarm robotics. For example, James McClure-Hemsworth at Rice University has done many different kinds of behaviors. So now we can start to program those behaviors on these robots as well and see if we can understand them. So in our group, we look at many different kinds of collective behaviors, some inspired by ants, or fireflies in this case, some inspired by cells. And the key element in all of these behaviors is that an individual robot actually doesn't have that much knowledge. Maybe it can talk to 10 robots in its vicinity, but it doesn't know what's happening all the way across. So any kind of algorithm, that information has to propagate. The other thing is they all operate at slightly different times. There's asynchronous, there's message loss, there's bumping, there's failures. And so whatever algorithm has to be able to constantly repair and constantly adjust to the fact that some fraction of robots will never do the right thing. So this is sort of one sort of fun video we had. But an example is collective transport. So very often you go to a place and you can see groups of ants cart off things together. They don't know the shape of your potato chip, but they're very good at making sure it gets to their nest. So how would you make robots that could go into an unknown environment and move things together without knowing the exact shape or without knowing the exact weight distribution of an object? Ants do it. Can we learn how to do it? Do we understand what happens when hundreds of robots do it together? This is just another example of collective behavior. Well, actually, this is individual behavior. So the robots have a light sensor. In addition to interacting with each other, they can sense light. So they're climbing up a chemical gradient. So how do you move up a set of information? And one of the reasons I like this video a lot, besides the fact that it's sort of fun to make plus with the others, you can see not every robot is the same. A lot of robots do the wrong thing. And a lot of robots do the wrong thing for a little time and then recover. You can clearly see that this one's really okay. There were a whole bunch that were sort of going in the opposite direction. Like, even if there have 10% of your robots misbehave, how do you make an algorithm that's robust to that? This is just another example. I know this is cycling through quite a different examples, but each of these are simple behaviors. Pattern formation, movement, climbing gradients, synchronization. These are kind of basic collective behaviors that we like to compose together and think that they're sort of basic behaviors that any group should have, and then maybe complex behaviors would compose those different behaviors together. So here we're using a very simple, well-known idea of pattern formation, where you have a source of information, and the colors represent how the information is flowing, how many hops the information has to go through the system. And that kind of tells you distance from the source. And so this just shows that those kind of patterns can be made self-repairing. So if I move the source, the pattern will adapt according to the source. Okay. So again, our goal is to be able to put these things together and make complex behavior. So here's an idea from Mike Rubenstein from his PhD thesis at University of Southern California. What if you could make sort of programmable material where you could program the individuals and then they could self-organize into whatever shape you wanted to get them. And here is Mike as of now. And our first set of experiments with a full 1,000 robots was to be able to create that kind of complex behavior. Can we get groups of thousands of robots without any human intervention to actually do some sort of very complicated behavior? And the key thing to know with this highly sped up movie, which you can tell is highly sped up because you can see like flitting around, is it took about 12 hours. So 12 hours of thousands of robots operating together, and you're not allowed to touch or move or interfere with any of the robots. And it turns out there are lots of things we didn't understand at all about what that meant. So the algorithm itself, how does it work? It basically composes some of the examples that I showed before, like pattern formation, robots orbiting other robots, forming coordinate systems. These are sort of well-known algorithms. But we also had to add a number of different things. What do you do when robots fail? What do you do when robots make mistakes? What sort of immune system do you add to the system to deal with all of the rare failures that are going to happen if you have 1,000 robots? So just to show examples, here's a simple edge following behavior. Well, you actually get traffic jams. You get traffic jams that cause so much congestion, everything stops. Every time the robots form patterns, they form it slightly differently. Many times robots stop and have to actually reboot and refigure out themselves. And maybe eventually we'd have to have groups of robots that cart off other robots. But with 1,000 robots, you start to see every rare failure that we used to be able to correct by taking the robot out. Nevertheless, we can make lots of different things now and program complex behavior with thousands of robots and start to understand experimentally what it's going to take to recreate or even create our own groups with these collectives that have large numbers of groups working together. Our group is part of actually a much bigger community that studies collective intelligence. So, of course, within robotics, there's many different examples of thinking about how robots can cooperate together. So these are two examples of different kinds of construction. So, for example, quadrotors building large-scale structures, or floating bridges that can basically form by self-assembling pieces together. There's more complex forms. We thought of just cooperation, but imagine that there's also competition. So, for example, robot soccer, or any sort of adversarial environment, like even with the case of the fires, where robots have to act under constraints. There's so many examples where we would like to be able to increase the number of robots working together. And on the other side, I think there's just a lot of scientific questions, too, that we can't necessarily understand by changing the brain of a fish or changing the brain of an ant, but maybe we can understand through engineering. So actually be able to build those rules, test them in robots, and understand how well do we understand the general principles that maybe we think are operating in nature. And I think in this way, both computer science, biology, and robotics have a lot to offer each other. And it's also very very fun. It means you can work in all disciplines and justify it and enjoy the experience. Okay, so with that, I was going to conclude. And the most important fact is that all of this research is itself the product of collective intelligence. So I have an amazing research team that I work with, and in particular, Justin and Kirsten are the two people I've worked with closely on the Termes project, so building termite-like robots. They've also traveled through India multiple times to help with studies of actual termites. And Mike is the one whose work I showed on the kilowatts, and also Alex Cornijo, who's worked closely with Mike on both the theory and the design of programming of these robots. And the kilowatts robots are actually available for purchase. So you can buy them from a company called K2. So now we actually have several labs that are using the kilowatts, and it's been a really great way to trade both algorithms and ideas and new insights. And that's it.
Do you have any questions?
Yeah, hi, great talk. I know very little about actual swarms, so biological swarms, but it seems to me that one of the things that you see in the natural swarms is that while each individual is somewhat limited, there are actually multiple roles, and there's often sort of a key player with an event or something like that. Can you just comment a little bit about how that fits back?
Yeah, and I think that's a super important part. So in some cases, they're definitely key individuals, and especially as you get to higher animals, like if you were thinking about groups of wolves, for example, or groups of mammals, there's often an inside hierarchy. With ants, in particular, they believe there isn't a hierarchy, but there is a task allocation. So often, they're never doing one task, right? Some of them are foraging, some of them are defending, some of them are nursing. And that task allocation is really important. So I don't know if it's because our group has chosen one task to focus on that we keep getting away with very homogeneous, identically programmed robots. But I think that as we get to more complicated scenarios, you would really want to have a situation where the robots are really fundamentally taking on different roles. Or another reason to take different roles would be because we physically need to build different robots. So maybe we have some climbing robots, some beam robots, some remove dead robots. And then it's really like having an ant where you have different physical casts that are basically need to cooperate to achieve something. So I think all of that is still on the horizon. And our goal was really to try and push this question of like how far you could get with a homogeneous set where there really wasn't any hierarchy. I mean, that's part of the question, right? It's a very good point. I think that heterogeneous systems are really important.
So for the Chinese robots, what kind of sensors do you put on robots?
So right now it's very, very simple sensing. When we started, we were trying to sort of follow the idea of embodied intelligence as much as intelligence is in a physical robot. So it has a tilt sensor, so when it climbs, it knows it's climbing. And so if it knows when it's done climbing, for example. That's something that helps it climb robustly. The hand sensor has a touch sensor, so it knows when it's physically touched or let go of the block, and that's used a lot. But mostly it has IR sensors that are facing downward, so that's how it sees the crosses on the block. So it's basically looking that it moves block to block. And that's part of its sort of navigation algorithm. And then it has some ultrasound when it's going around. But that's basically everything. I think it's probably true that you could use depth cameras or something would be a much more efficient way currently of doing it. But we started out by trying to create as minimal robot as we could.
So when they're too close, they use the IR sensors?
They actually use the ultrasound. So the ultrasound that they're using for distance measuring, they just send a very loud beam, which basically is like get away. That's basically.
And also how, what's the real speed? I see 20 times better. But
Yeah. So the video that I showed of making the castle, which they're not building the whole castle, they're building part of it, is basically half an hour. Yeah. So I mean that's one thing. Is in a talk you don't want to sit through half an hour, but they are still really slow. And the kilowatts in particular are slow with the vibration motors. That was sort of a cost. That makes the cost really drop, so it was worth it. But I think getting autonomous robots to be faster is actually still super hard, and I don't have a good feeling for like what we need to learn in order to make that happen? Is it just having a better sensor, a better body? Or is it that we're just fundamentally thinking incorrectly?